So if we're looking at a reduction reaction, that is going to be one where, if you remember the oil rig, reduction is gain. We're going to gain hydrogen across CH bonds. This will result in a gain of hydrogen. Okay, so in our reaction, we have a reduction. We're going to keep our carbon skeleton the same with the oxygen, and here we're going to add hydrogen across the double bond to get an alcohol. So H2 is added, and we're also decreasing the number of CO bonds. So we're gaining H2. And we went from 0 CH bonds there to now we have 1 CH bond. So from an aldehyde, if we do a reduction, we're going to add H2 across the double bond. And this will result in a primary alcohol. If we use the ketone, the reaction is similar. We add H2. And this will be a secondary alcohol. Aldehyde with H2 palladium, this is our reagent that we've already seen before. We use it to reduce double bonds. We can use it to also reduce aldehydes. So we're going to add H and H here to get a primary alcohol. And then with this ketone, we're going to use H2 and palladium. I'm just going to draw this out here. This is what it looks like before. I'm going to add my H's here to get a secondary alcohol. So before, when we did this reaction with alkenes, we added H2 palladium. That added H's across the double bond, which is exactly the same thing we're doing here, except one of our double bond atoms is an oxygen instead of a carbon. Okay, so what alcohol is formed when each of these is reacted with H2? So I just told you that using an alkene with H2 palladium is going to result in adding H's across that. So we're going to do H's across the carbonyl. We're going to add H's across the carbonyl and also the alkene. And then with the aldehyde, my carbon skeleton is the same. There was an H here before, and I'm going to add a couple more. Chemists can synthesize compounds, including medications, often using these functional groups. So here is a typical ketone. We're going to do a reduction reaction. So H2 will not react with benzene, but it will react with a ketone. We're going to add H here and onto the alcohol. You don't have to draw in the H on the carbon part, but you do have to draw it in on the alcohol. So after several steps, after you've now made the secondary alcohol, we can synthesize fluoxetine, which has the trade name of Prozac. So what product is formed when muscone is reduced with H2 and a palladium catalyst? In muscone, we have a ketone. We have a secondary alcohol. This is going to undergo some reduction reaction, but it won't use H2 palladium because this was left alone. And then 4 steps later, we get muscone, which is the odor of musk. And if we reduce this with another reduction reagent, so let's say we use H2 palladium, so that those bonds were removed in that compound here. So now we have to draw this funny structure. All right, and then we're just going to get an alcohol added here. In biological systems, we definitely don't use H2 and palladium. That's just not safe. Instead, we use a reagent called NADH, or nicotinamide adenine dinucleotide. So in this biological reaction, we have some ketone in our biological system. We use NADH, which is a coenzyme that will add our hydrogens here and here. And that H was removed from NADH, so that becomes NAD+. So this NADH is synthesized from niacin, or vitamin B3, and that can be obtained from soybeans, among other dietary sources. And then pyruvic acid, we'll see later on in the semester, is one of the byproducts of our biological cycles. That, in combination with NADH and lactate dehydrogenase, which is another enzyme, will reduce this ketone into this alcohol here. And then we'll get NAD+ again as a side product. Another reaction that we'll encounter with ketones and aldehydes is acetal formation. So this reaction can be done with a ketone or an aldehyde, which is why that R is written in parentheses there. This involves an alcohol with an ROH, so it can be any alcohol in the presence of acid or H2SO4. The thing that happens first is we're going to form a hemiacetal. So I have my H here, I'm going to put R in parentheses. And I'm going to form an H to make the alcohol, and there's going to be this ether here. So this is a hemiacetal. And this is an intermediate. These reactions are reversible, so they can go forwards and backwards. And so what I've done, I have my scissors. I'm going to chop this in half right at the oxygen and split those two apart. So one oxygen from the carbonyl is going to get a hydrogen, and then this OR is going to attach right there. So that's my new bond. This reaction can happen again with another molecule of the alcohol in the presence of acid. So now I'm going to remove this guy. That one is going to go away. So I have R and the H with the R in parentheses, my OR prime that was already there, and then I'm going to use the green one to show that the second one got added. So this is the OR prime. So let's just make this green too. And then my side product is the water that forms from all those extra protons that are floating around. So this is called an acetal. So first I cut my carbonyl in half. I put one alcohol on there, and then I kicked the second one off and put another alcohol on there. So that's an acetal. A hemiacetal has one C that is bonded to one OH and one OR. An acetal has one C that is bonded to two OR groups. Okay, we can look at a couple of examples here. What acetal is going to be formed? We're not going to worry about the hemiacetals. We're just going to worry about the acetals. This is an aldehyde. We'll just write that here. I'm going to take a scissor, which kind of looks like an acetal, and I'm going to chop right down there. So here's my carbon skeleton. You can just split the two bonds apart and put in its place an O, CH2CH3, and another O, CH2CH3. This is the acetal that forms. And then you also have water as a side product. In this next example, again, you can think of chopping off that carbonyl, and then we're going to split down the middle here. So we draw our cyclopentane. I've cut off the oxygen. I'm going to split the two bonds and put these in its place, and then plus water. You only have to worry about the product of the acetal. The water is there just to know where things have gone, but you don't have to put those on there. With cyclohexanone, methanol is going to be our ROH. So we're going to start by clipping this off for the hemiacetal. I have the OH here with the ethyl group, and the hydrogen comes from there. This reaction will keep going. I'm going to draw the second molecule of ethanol in green so you can see where that goes. So this is the one that was here, and then we're going to replace the other alcohol with this ethanol. So here's my acetal, and our water is the side product, and this is the hemiacetal. So the hemi is the OH and the OR group, and the acetal has two OR groups. When we do this with cyclopentenone, the same process. To do the hemiacetal, we're just going to do a snip here. But here, my alcohol is going to stay connected over here. I have this H, and instead of using a different alcohol, this one right here is going to come and kick off that OH. So we're going to lose the water. I have this O. There's two carbons in between, another oxygen, and here's my new bond. And this was the other oxygen. So that one's going to form a cyclic acetal. So here we're going to determine if these compounds are ethers. hemiacetals or acetals. So ether, if you remember, is an oxygen between two R's. A hemiacetal has a carbon with an OH and an OR on the same carbon, and the acetal has two OR groups on the same carbon. If I look at this compound here, I have an oxygen with a carbon here and a carbon here. So this one is an ether. This carbon right here is bonded to an OCH3. On the same carbon is an OCH3. This one is an acetal. And this one right here has an OH and an OCH3 on the same carbon. This is a hemiacetal. We can also get cyclic acetals, which we saw in the one example. These are both cyclic hemiacetals. The hemiacetal carbons are bonded to one OH and one OR group. Where this part is the R. And that's what makes them a hemiacetal. So if you have an aldehyde and an alcohol in the same chain, the alcohol can wrap around and react to form the hemiacetal. So if this is the aldehyde, 1, 2, 3. So there's the alcohol that is close together so they can react to form the hemiacetal. There's the oxygen, forms a new bond here, and then we have the OH added up top. So this is the hemiacetal. Once you have a cyclic hemiacetal, if another alcohol is introduced, that can replace the alcohol and form a full acetal. So I can add an OCH3 here to make the acetal. So we'll see acetals and these sugars later on in the semester, but this one here is lactose, which is the principal carbohydrate in milk. This one has one acetal, which you can see here, the carbon bonded to two OR groups. And it also contains the hemiacetal, which has an OH to an OR. Many individuals, mainly of Asian and African descent, don't have the amount of lactase needed to process lactose. So a lot of these people are lactose intolerant. This condition is associated, as you may know, with abdominal cramping and recurrent diarrhea. Other places we might see cyclic hemiacetals are in a compound called solanine. This is formed in the leaves and stems and green spots on the skin of potatoes, and it's a defense mechanism for potatoes against insects and predators. So here we're going to look for all of the acetals in the toxin solanine. So when we're looking for an acetal carbon, we're looking for a C with two OR groups bonded to the same C. So this one right here, if I looked at carbon, let's call this A, I have a C bonded to an O and a C bonded to the C, so that's not one. But if I go here to B, this one right here is bonded to an OR, and that same B is OR this way. Okay, so B is an acetal carbon. Another place that I'll see one is right here. I'll call this C. I have an O to an R, and then an OR here. So this is an acetal carbon. And this one here is also an acetal carbon. So on that one, I have an OR, and then an O to an R group there. So that's another carbon. So we have 3 acetal carbons in solanine. Okay, a reaction that we can do with acetals is hydrolysis. Hydrolysis is the reverse reaction. So if I'm going to reverse a reaction, in order to make the acetal, I started with a carbonyl, so ketone or aldehyde. And by reversing the reaction from an acetal, we're going to get the ketone or aldehyde back. So you can think of this reaction as just removing these and replacing it with the double bond O. So just trim those off. I'll have an R to my H and the R in parentheses in case it's a ketone. And the next thing I'll do is replace it with a C double bond O. So when we do our acetal hydrolysis, it's a reverse reaction. We started with the ketone or aldehyde, added some alcohols to get the acetal, and when we add acid and water, that goes back to the ketone or aldehyde. So if I look at this example here, I'm just going to trim that off. I have the same carbon, and I'm going to replace it with a C double bond O. So I'll get that compound back, plus 2 OCH3 H's. So those came off, and up here this would be HOR prime, and there's 2 of those. And then for this reaction, we're going to trim those off. We get cyclohexanone plus ethanol. So in this reaction, we're looking to see what is formed by hydrolysis. So it's asking us if we add H2O with H2SO4, what's going to happen? The first step here is to find the acetyl carbon, and we're looking for carbon that is bonded to 2 OR groups so that we can do the hydrolysis. So 2 OR groups on the same carbon. This is an OH over here, so that's not going to be the correct one. This is my acetyl carbon. So this one's kind of tricky here. So I'm going to draw this skeleton. So this part is going to be one alcohol. This is going to be an alcohol. So this is an alcohol here. This is an alcohol right here. And this one was one, but now that becomes the carbonyl. Plus my alcohol is OCH3 that got cleaved off. So that one is kind of tricky because it's cyclic. And there's my acetyl carbon. That one gets freed from there. In another way that you can think of it is if these weren't connected, you had an OCH3 So I'm just going to pretend for a second there that ring is not a ring. These would get cleaved off. So I have OH. I have a carbonyl and then the OCH3. And then I'd have the other O that went to here. But now we know that that one was connected to here. So that's how I get that one with the OH here.